That's what you do, bro. Then the x is now the new x. 0.0156. Number one.
All right, let's continue. Now, next lesson. Can you see okay? Young's modulus. You got that? Marwan? You got that, guys? Yeah. Continue? Okay, so. Does anybody know this word? The deformation of a material.
Change its shape.
Yeah. The deformation of a material is the process of changing the shape. For us, though, that will just mean changing the length. By applying what's called a stressing force. Okay, you should write that down. You got that?
Yeah.
Okay. Continue. Now, the word stress actually has a physics meaning here. What we say is the stress on a material is the force on the material per cross-sectional area. Now, this should remind you of something. It's like pressure, isn't it? So what's the units for stress? Pascals, yeah. And what's the formula for stress? Yeah. Therefore, the units are clearly pascals. Okay?
Okay.
Continue. Yeah? Now, another definition is strain. I wonder if anyone knows this one. Did anyone know stress? Or no. Strain. The strain on a material, do you think, does anyone know?
You pull your muscle up that sense.
Yeah, we need the physics definition though.
Extension over length.
Is that a guess?
No, I've heard it.
Yep, that's it, yep. Strain is the extension per length. So, as a formula, well, there you go, X over L. And so, what are the units of strain? Yeah. I could hear your brains thinking about that. Okay? Continue? Yeah? So now we can finally get to Young's modulus E. Yeah. I was just thinking if there's another letter used. I think it's usually E. I think they use a different letter sometimes. Anyways, Young's modulus, whatever letter you want to use it is the ratio of stress to strain. That is, it's stress divided by strain. What are you saying, man? Where you get? What's this word here you keep saying?
Flea.
The heck?
F-L-E-A. Force times length over extension times area. Flea.
What? And that represents?
Stress over strain.
Okay.
F-L-E-A.
Okay. Whatevs.
Just ahead there's no E's. X.
Yep.
Call it.
Continue? Yeah?
Yeah.
What's the units for E? Right, tensile strength. Does anyone know what that is? Anyone? Oh, come on, man. Make it a bit more technical than that, alright? It's like you said, what's tensile strength? You know, it's the strength of a tensile. Give me something more detailed. Good. Now, strength doesn't have a definition though in physics, so you need to change that word.
The amount of energy.
Not energy. It's the measurement of force required to pull something like a rope to the point where it breaks.
Mm-hmm.
Okay. You got that? Yeah? Yeah? Son?
This has that word.
Okay. Okay.
Yeah.
Now, let's look at a stress against strain graph. Okay, so there are three types of materials we look at where we have stress and strain. This reminds us a little bit about force and extension. Strain, what's strain? Which one's strain? The formula? Extension over length. And stress? Yeah. So as you increase the strain, which is usually the extension, then you increase the stress. But some materials behave differently. Like, for example, this material here, where you increase the strain and you don't get much more stress, that's a plastic material. This material here, where you increase the strain a little bit and you get a lot of stress, that's a brittle material. That means actually it'll break quite easily now. This middle material is what we were looking at in the last lesson, is actually called a ductile material. What's the name of this part of the graph? Elastic region. Okay. But then we reach a point where it no longer behaves properly, past its elastic limit. Yeah? Don't worry too much about the shape. The point is it's now oddly behaving. Because you can imagine you can stretch the material so much it's almost like, sometimes your clothes are elastic, aren't they? They have a stretch in them. But sometimes if you dry them too high in the dryer, then they come out and they lose their stretchiness and they're all kind of weird shaped then, You sometimes have to draw this graph in the exam, so can you copy this in your notebook, please? Yeah. Okay, continue. Yeah. What I want to do next. Oh yeah, actually I should say, I didn't say this, but the slope of this graph, what does that represent? What's the slope of this graph representing? Can you note that? Slope equals Young's modulus. Okay? Continue? Yeah? Okay. Now, what I want to have a look at now, briefly, before we continue, is what is the relationship between stiffness constant K and Young's modulus E. So you have Young's modulus is stress over strain, which equals force over area over extension over length. But Hooke said F is Kx, didn't he? Over A over X over L. What cancels here?
X.
So that's K over A over 1 over L. So, you're right? So you multiply by L's and you get KL over A. Yeah? And I'm trying to think of a way to remember it. You could say something like EA, games, equals, which would be better, KL or LK?
So it has no DLC for the formula, right?
No, no DLC necessary. Everything's included. Do you like EA? There we go. LK equals EA. Maybe that will help you remember it. Now, this formula is not in the formula book, but sometimes it's useful to have a way to convert between E and K. So if you like EA, you can use this formula. Okie dokie. Continue? Yep. Now, I'm going to give you some values of E you can write down. So, the unit is pascals, of course. So the first material is rubber. Now, is rubber a stretchy material? It is, isn't it? And it has a Young's modulus of 0.1 times 10 to the 9. Now, that's actually a small, isn't it? Sorry. Yeah, it's a small value, even though it's 10 to the 9. Okay. Can you write that down? Yeah. Next material is nylon. You all know this material? Yep. Next material is wood. No, actually, there's not. You know, it's funny. There's not a big difference between wood and these materials. So wood is a little bit stretchy. But you kind of know this already. Like, you could take a piece of wood and sort of manipulate the shape a little bit.
I thought wood would be brittle.
It is. I think you would have to slowly apply the force, or you'd snap it. Okay? But, Bello, if you had a plank of wood, you could wrap it into a circular shape slowly. Like nylon or rubber, you know. Next material is glass. Now you see we're starting to get bigger. And then, it's very brittle. Next material is brass. And you see we're increasing the values now. Next material, copper. Metal here. See them getting bigger and bigger. Steel, and then surprisingly big is graphene. It's actually quite big. I was surprised by this. Okay.
What's graphene?
Like in the pencil, isn't it?
Yeah.
Graphite.
Yeah. You got that? Yeah. Continue. Yeah.
Wait a second. 3 left. Okay.
Yeah.
Go ahead.
Right. Okay. Time. Okay. Right. We'll run through this one quickly. A boy hangs 100 grams at the end of a 1.5. So the only value you need here is the copper one. He hangs 100 grams at the end of a copper wire of length 1.5 and thickness diameter of 2 millimeters. Okay? A. What's the area of the wire? So it's, if you think about the wire like this, it's this area. So what formula do we need?
Pi r squared.
Pi r squared. What's the r?
0.001.
1 millimeter.
Sorry.
Go get it. 0.001 squared. Right, what's that, please?
3.1
3.14.
times 10 to the minus 6.
Oh yeah, of course it is. B. What is the stress? Okay, what's the formula for stress? What type of force is this? Gravity. 0.1, so that's 0.981 over 3.14 times 10 to the minus 6. So what's that?
Three, one,
3124. So it's 312 kilo Pascal. C. I guess I'm going to ask for the strain next. Yeah. What's the strain? It's X over L. Do we know X? No. Do we know L? Yeah, so we can't really use that formula. But we could use Young's modulus. Is stress over strain. So then what's the strain? It's stress multiply over Young's modulus. What's Young's modulus for copper? 117. Okay, so what's that now? 2.60.
7.
2.67
Yes.
times.
10.
Minus 6.
Okay. How much has the wire extended? What's the extension? Strain equals X over L. Yeah. So X is going to be strain multiply 1.5. So what's that? Four times 4 micrometers. Yeah. Okay. And lastly, E, what's the K? So if you like EA, you can get the K. K equals EA over L. So that will be 117 times 10 to the 9 times 3.14 times 10 to the minus 6 over 1.5 equals
245.
But
245?
3 zeros.
So 245 kilo newtons per meter.
Is
Yep.
this as hard as it can get?
Yep. It's all right, actually.
Just from your
It's just formulas. It's just formulas. That's all there is. Okay. One thing left to do. So I just about have time to talk about the experiment you need for this, which is how do you calculate Young's modulus for a material. I can think of a couple of ways to do it. So suppose you want to calculate the material of, I don't know, copper, or whatever it is. Can I scroll down? Yeah. So, what things would you need? You would need, so your equipment, you would need a way to measure the diameter of the wire. Oh, hang on, I know what that's called. It's micrometer, isn't it? Yeah. You need a micrometer. A micrometer is the measuring device used to measure thickness of a material. Have you seen them before?
Yeah.
They're like little clamps. You put them in and it measures the thickness. They're called micrometers. You also need something to measure the extension, so just a ruler. You'll also need a wire of the material. So for example, if you want to measure Young's modulus of copper, then you need to use a copper wire. You want to measure Young's modulus of steel, then you need to use a steel wire. Yeah? And then lastly, you need clamps and a box of weights. And what's the diagram? The diagram, what you do, you have your ruler, and then you have your clamp here, then you have your wire, then you have your weight hanging at the end. Oh, and then what you can do is you can put a little like flag here, and then that way you can measure the extension by seeing how much the wire moves. So what's the method here? Well, number one, you would set up as sorry. First thing you should do is use micrometer to measure radius, and then after you have that you can calculate the area. Yeah? Then what you can do is hang different weights and note extension. Then what you can do is calculate stress, because stress would equal the force, which is the weight, over the area which you calculated. Then what you do is you plot stress and strain, and the graph looks like this, doesn't it? What did we put here? Stress, wasn't it?
Yeah. Oh,
strain, was it? And then here,
stress.
stress. And then finally, after you plot the graph, you have your result. Young's modulus will equal the slope. Then you can get Young's modulus from the graph. Sorry, I can read this if you have trouble reading it. I'll read the method, okay? Use micrometer to measure radius or. Calculate area A. Hang different weights and note the extension X. Calculate stress equals W over A and plot stress against strain. Calculate stress and also calculate strain.
Does it will happen in exam?
Say again?
Does it happen in exam?
What do you mean?
They ask us
question.
for this.
Could they ask you this?
Yeah.
Yeah, they could ask you a question like this. They could say, describe an experiment to determine Young's modulus of a metal wire. Now, will they ask you that? I don't know.
Probably.
10% chance.
Mm-hmm.
10% chance? Is that big? It's 5 times more than the coronavirus.
Is the English plot stress against strain?
Yeah, I just used a hyphen.
What's about the physics essay?
After lunch, we'll talk about it at the end of the class. Right, once you have that, you can start the questions for 5 minutes. And so I do not forget, who is resitting the test this afternoon? How many of you? 3 of you, is it?
Mm.
Which test?
Physics only. Physics. Math.
Math.
Both?
Yeah.
Both?
Math.
Okay. There's 4 of you, is it? 4 of you? Yeah. All right. If you have that, please start the questions for a few minutes.